That gives me lambda. So that is the conclusion. The variance of x is also lambda. So the mean and the variance of a Poisson distribution is the same. Why can't you try this on your own? What if I ask you to derive this guy? Try that on your own for Poisson distribution. Okay? Okay, so that is going to be the end of deriving the mean and variance of probability distribution. Now I want to go to the second objective of the day, moment generating function. Now let me tell you this: we got more than one method of deriving the mean, variance, and so on from a given probability distribution. Okay, the method we'll be using on this y is what we call the method of movement. The method of movement. But another method that can be used, okay, that will save time, except that you actually need the idea of the calculus, is what I'm going to call the method of moment generating function. So I want to welcome you to method of moment generating function. Okay, the method of moment generating function is another way of deriving the mean, the variance, and whatever we want to derive from a given probability distribution. Okay, so moment generating function. Okay, if I have a random variable s, okay, a random variable s that comes from any of the discrete type probability distribution, it could be by Bernoulli, binomial, negative binomial, and so on like that. And of course, the moment generating function can be derived. But let me tell you this: some distributions do not have moment generating function. Like we don't find moment generating function for hypergeometric distribution. Please take notes. If you want to derive the mean and variance in hypergeometric distribution, we're basically going to use the arrow moment approach. Okay, but you know what? Let me welcome you to moment generating function. You know, in the moment generating function, we have ms of t. Okay, we got to expectation of exponential raised to power tx. Okay, now this is the such that the t that I'm talking about lies between a negative a and a. A is a constant. Okay, now for any given distribution, the moment yeah, go ahead. Is that what? Exponential. Exponential. I mean this guy. Okay, now if you take a look at, let's take a look at this. If I have e raised to power tx from Taylor series, it's going to be tx raised to power 0 divided by 0 factorial, tx raised to power 1 divided by 1 factorial, tx raised to power 2 divided by 2 factorial, and that goes all the way, right? Take a look at that. Now, if you take a look at this guy now, okay, if I want to write that, it's going to be 1 plus tx plus t squared s squared divided by 2, right? Okay, now let me now take the expectation. Okay, we want to take the expectation of all of that. Like I said, before you come to this class, you actually have prerequisite, right? If I were you, why can't you revise the prerequisite knowledge? Now, if I take expectation now, expectation of this, okay? Expectation of that, expectation, of all of this. I'm actually, I told you that expectation of a constant is a constant, why? So here, plus t, expected value of x, right? Here, plus t squared, okay, over 2, expected value of s squared, and that will continue to go, right? Like that. Okay, that is the expectation that I'm actually talking about. Okay, now when we set t to 0, if t equal to 0, what does it give? If t equal to 0, what I'm telling the world is mx of 0, expectation of this of 0, okay, plug in t to be equal to 0, that is going to give you 1, right? There's going to be t in every of the expression, right? When you set t to 0, that's basically going to be 1. Okay, now let us now see whether, and that very 1, oh, that very 1 is more or less that we're trying to say, whatever distribution that we use this for is valid. When you want to prove for validity of a distribution, okay, if it is discrete, the sum of that must be equal to 1. You remember what we've been verifying, right? Okay, if this is it, then the idea of the mean variance can actually be derived from this. How? Let's take a look at it. Let's take a look. Oh, okay. Let's do the first derivative. The first derivative of this. Okay, this guy here is mx of t. Okay, if I do this with respect to t, okay, with respect to t, okay, which is, I can rewrite as, when I indicate this sign, mid derivative. Now let's do that now. Well, let's differentiate this with respect to t. Okay, when you differentiate this, this is going to be 0. This is going to be expected value of x, right? Okay, this is going to be 2t over 2, which is going to be t, expectation of s squared, and so on like that. When we do that, and we set it to 0. Now, if I set t to 0 now, d dt mx of t, and I set t to be equal to 0, what happened? Set it to 0. This go to 0. Every other one that with t go to 0, what do you have? Oh my God, look at that. It means when I differentiate moment generating function first time, and I plug in 0 for t, that will automatically give me the mean of the distribution. Does that make sense? If I now want to get a variance, what am I going to do then? What I'm going to do, if I want to get a variance, I only need the expectation of s squared. Okay, now the expectation of s squared is going to, what we're going to do is that we require second derivative. Tell me, if there is no mathematical knowledge, then there can never be statistics. If there's no statistics, no research. Because now look at the formulas that we use in statistical analysis. We use the first principle, of mathematical theory to derive them. Now, what I'm trying to say now, the other time when I differentiated, I have this. If I want to continue, if I do the squared mx of t, the t squared, for instance, okay, I actually go here, right? Okay, when I go here, when I differentiate again with respect to t before plugging in 0, this is going to have a t. We still have some other t, right? Okay, now when you differentiate this guy, of course, that would be 0. What am I going to have? I'm going to have expected value of what? S squared, right? So which means, okay, even in the other one, of course, in the other one, there's going to be t, right? There's still going to be t, right? But when you plug that t to 0, automatically, this is what you're going to have. Oh, okay. If I continue to go, the t raised to power 3 with t equal to 0, that would be expectation of this guy. If I now go to generalization, where I'm actually now consider the case, or let's say R, okay, R ms of t, okay, the TR where T equal to 0, this is going to give me expected value of that. Take a look at that. That is a generalization. Therefore, this is a function that generates moment for us. Then when we have moment, then we're going to have the mean variance and so on like that. Now, I want us to practice this on some distributions. Please make sure you wash out your mean time too. Okay, you can be given any probability distribution and ask you to derive the moment generating function for that distribution, and from the moment generating function obtain the mean and variance. Now let's try one. We're gonna try one now. We're gonna try one now. Let me start with binomial. Okay, now binomial. Okay, binomial x follow binom. Okay, parameter MP. Okay, the probability of this guy equal n combination x, p raised to power x, 1 minus p raised to power n minus x start from 0, 1, 2 to n. Okay, and the question is asking you, use the method of moment generating function to derive the mean and variance. Or we can even ask you to derive the moment generating function. Okay, I need you to focus now on the board. Those of you online, can you still confirm if you are seeing what I've been writing on the board?
Yes.
Okay, thank you for confirming that. Now, I need you to be more focused now. I want to obtain the moment generating function of a binomial distribution. Okay, and of course, the moment generating function is this. Okay, expectation of that for discrete is going to be summation e raised to power ts, the probability of this, where s start from 0 to n. Look at my interpretation now. When I was doing expectation of x, for discrete, it was summation x that, but right now, expectation of e raised exponential raised power ts is going to be that. Now, if I have this guy now, okay, so if I have this guy now, okay, the ms of t, okay, 0 to n, e raised to power tx, this guy, the binomial distribution, n combination s, p raised to power x, okay, I may decide to use instead of 1 minus p, I can use q, okay? So q raised to power n minus s, take a look at that, okay? Now, if you take a look at this, I can rewrite this as this, okay, n combination x, okay. Now, when you take a look at what I have here, and what I have here, okay, you basically going to see that if you take a look at this guy and this guy and this guy has a, you have a q of that, okay. Now I can combine this and this. I can do e raised to power t p or raised to power x, okay, and q raised to power that. Any question? I only combine this and this. They both have that. Okay. After combining this, the next thing that will come to my mind, I will have to travel back. I want to travel back to where? I want to travel back to what I've done before. That has to do with binomial expansion. Let us recall from binomial. There's something that we call binomial expansion in mathematics. Has anybody has about Pascal triangular formula? Okay, now if I have this, a plus b raised to power n is the same thing as summation, okay, and combination x, okay, a raised to power x, b raised to power n minus x, s start from 0 to n. We're recalling this. Oh, let us compare this with this guy here. Look at this, is here. Look at this, is here. Look at this. This is scaling S. This is scaling S. What does that mean? A equal to this guy, right? So I'm going to write that now. So you're going to see, oh my God, mass is easy, right? Mass is easy. So what I'm going to do now you are comparing. That implies A equal this, right? What is B? What is B? B equal to Q. If you compare them, B equal to Q. Now, if this guy equal A plus B raised to power n, then I can rewrite that guy. I'm going to write ms of t, okay, equal, okay, what is my A? A is this guy, okay, then plus, what is my B? Q, everything raised to power what? N, okay, you see that? Like I can rewrite that as Q, if you want to start from Q, and P, E, T, anywhere in the world. This is the moment generating function of binomial distribution. That is a moment generating function of binomial distribution. Now, if this is a moment generating function of binomial now, can we use this moment generating function to derive the mean and variance? Let's see. We can do that. Okay? We want to derive the mean and variance from that. Okay? Now, what I'm going to do, I will need to do the first derivative. Because you know why? Mean, expected value of x, in terms of moment generating function, is d dt ms of t, where set t to be equal to 0. This is the expected value of x. And expected value of s squared is going to be d squared ms of t, the t squared, t start from that is going to be, so this guy here is, and you know, the moment I got this guy, of course, I can find my mean, I can find my variance. Now, let's look at the mean first. You have that expression. Okay. You have that moment generating function given, right? We want to differentiate this guy. You need to go back to calculus. How do you differentiate a function of function? Okay, so d mx of t dt is going to be, don't forget, I'm differentiating with respect to t. Okay, I'm going to have n, I'm going to block it, differentiate what you have inside with respect to t. That will be this guy. I'm going to rewrite the whole thing. Then this is going to be that. Then what am I going to do next? Plug in t to be equal to 0. Okay, now dnx of t dt, okay, with t equal to 0, let's see, n p e raised to power 0 q plus this e raised to power 0 this. Look at that. What do I have? This is 1 q plus p. Oh my God. MP, what is q? What is this? 1, right? 1 is pi 18, 1. What is that? MP. That is the mean of binomial. You see that? Is that not interesting? Look at another method that we use. The method of moment generating function actually works so great. If I want to continue now, I want to get the variance, right? I will need to obtain this guy because you know why? The variance of x is expected value of x squared minus expected value of x all squared. Right now, I've gotten MP all squared. Okay, I need this guy. Okay, Maybe I will leave you to obtain that. Oh, my time is going so fast. Okay, I will quickly rush and do that of poison before I go. I'm gonna do that of poison. If I don't do what I'm doing now, if I'm just showing you the lecture slide, then you may not learn anything at all. It's a theory of statistics. I need to do what I'm doing now. Okay, so if I have a Poisson distribution, for Poisson distribution, okay, we are X follow poi with parameter lambda. The probability is this, right? Okay, we are S start from 0, 1 up to infinity. Okay, what is the moment generating function? The moment generating function is going to be this, which is equal to this, S start from 0 to infinity, e raised to power this, the probability of X equal to that, then I'm actually going to have S start from 0 to infinity, this guy, exponential raised to power this raised to power that divided by X factorial. Okay, if that is what I have, okay, if that is what I have, if that is what I have, okay, in order not to, this is page 1 for Poisson, so that you will not confuse that with that. And this is page 2. Okay, where are we now? And x of t equal, okay, I'll bring this guy out, right? Then I'm going to have s start from 0 to infinity. I can combine that guy, lambda e t, okay, all divided by this. Oh, I want to use that method again. This is x factorial, right? Okay, so here, this is going to be exponential carrying all this. If you combine this guy now, okay, lambda, this, minus lambda, what do you have? This is the moment generating function. If you derive any moment generating function that you want to know whether you are right, you know what you're going to do? If you want to know whether you are right, if you plug in 0 for t, your moment generating function should give you 1. Let's do that. Plug in t to be 0. This is going to be exponential raised to power 0. That will be 1. That's how you can check whether you are right when you derive any moment generating function. Okay. Now, this is a moment generating function. Now, if I want to obtain the mean, I only need to differentiate. I only need to differentiate that guy. Okay. I want to differentiate this guy. Okay. So d dt mx of t equal, okay, if I want to differentiate this guy, okay, I'm going to have lambda e raised to power c, okay, differentiating the guy, this is going to be 0. You're going to have that, then exponential lambda e raised to power t minus lambda. Okay, now what you're going to do now, d dt mx of t equal to 0, that is going to be this guy now, right? Lambda 1. What is that? Oh, my time is okay. Is there any question? Is there any question? Oh, go ahead. Oh, that's a very good question. In mathematics, we've already defined for moment generating function. T has to be between negative of a constant and a positive of a constant. And what is that? That's 0, right? That's how we've been plugging in 0. If t is not 0, moment generating function is not defined. That is just it. So in mathematics, statistics, we normally have we have assumptions. Okay, so assumptions is what make our model to be great. So what you're telling me now is will lead to what we call assumptions violation. And when assumptions are violated, what happens? You cannot trust your model anymore. That is similar to this guy. commit an offense in Minnesota, right? Can this guy be tried in the state of California? No, because the state of California does not have a territorial jurisdiction. It means assumption is violated. So in mathematics, when assumption is violated, if you go ahead and use that, then you will mislead. That's a good question. Very good one. Anybody online with question? Okay. This another, today is Thursday, right? Okay. Just like what I used to say. This is the end of the third week. Yeah, end of the third week. I need a message from you. I want to get a feedback. Tell me what is your understanding of the week. Like you tell me your understanding of the week and the understanding of the course in general. Okay. I'm going to be expecting your feedback. Feedback helps a lot. That's what keep me going. Okay. Make sure you all stay safe and enjoying your day. Bye for now, everyone. See you on Monday.
Thank you.
You were